Hey Harsh, it's great to meet you and thank you for attending interview with me. Let's listen to your story. So why don't you tell me about yourself?
Yeah, sure. So I'm computer science master student at UT Dallas. I have completed the courses of machine learning, big data, web development, then database design, and I'm also a TA for computer architecture and big data in UT Dallas. Uh, During my internship with Moody's, I developed server-side validation tools for their lending cloud product, and I use Silk Test and MS SQL Server for the purpose of the database. And then in during my internship with Sculptsoft, I was working as a software engineer intern, and I developed e-commerce scrapping, that is web application, and we used JSP servlets, Hibernate framework, and as a database, I used MS SQL Server.
Mhm.
And yeah, so this is basically my brief introduction from my.
Sure, that sounds great. All right. So you have mentioned that you have taken database design. So can you talk a
Yes,
little bit about database indexing?
database indexing.
Indexing. How do you do indexing in database and what's the purpose of
Uh, yeah. So basically, we used indexing for searching in the faster way. So there are like there are two basic main type of indexing in the database, that is non-clustered and one is the clustered one.
it?
The I think clustered one is on the primary key, right? I'm confused right now in between two of them.
That's fine. That's fine. What's the basic purpose of indexing? That's what I want to understand.
Yeah, so basic purpose is like if you want to search a record in the database and you have a millions of records in the database.
Got
So
it.
suppose you have to search like Harsh in the database, first name as a Harsh,
Mhm.
and you have a millions of records. Then if you go one by one for one row and second row and third row, if you searching like that, then it probably might be taken a very long time to search that particular record. But using the indexing on first name, if we do, so what it will do, it will just take the row number
Got
from
it.
which
Mhm.
wherever the hash is stored, then it will just fetch that particular record. So
Okay,
it will reduce the time in the searching manner.
got it. So you mentioned Angular JS as well, right?
Yes.
Okay, so how would you define that technology? What does Angular JS do?
Mm, so
What it
in
is
terms of
used for? Why do you use Angular?
yeah, so basically it's like a front. If you want to perform um so basically the front end it's a front end technology. So how to define this in how to put this in words? Mm,
How is it different from the traditional HTML, CSS kind of scenario or jQuery? Why, if I have to choose between a technology, let's say jQuery or
mhm.
Angular or let's say React, um, what will be the advantages that I'll be getting out of Angular or React rather than jQuery?
uh, Actually, I use Angular in just one project, so I'm not pretty much sure
Sure,
that
that's
how
that's
to
that's
make a difference between jQuery and AngularJS.
got it. All right. Let's move to the coding part of
Yeah,
the
sure.
share. All right. All right. So
Yeah,
take your time, read the question. I'll be silent if you have any questions for me, then to ask me.
yeah, sure, sure. Mm, the container with the most water, right?
Yes.
Okay. So given n non-negative integers, okay. where each represents a point of coordinates I and AI, and vertical lines are drawn such that two endpoints of line I is at I, comma AI. Okay, and find two lines which together with x-axis from container such that the container contains the most water. Okay, you may not slant the container and okay, so basically we have given some height of plates, and we need to find that what is the maximum water that uh, we can accommodate with any two plates, right?
Right.
Okay, okay, and mm, yeah, so basically we pour the waters from the top, right? And so water will level will be increased, and whatever the most uh, yeah, yeah, I got the question. Mhm. Yeah. mm, yes, so one approach that is coming to my mind right now, that is how to do this. Can I use my note and paper?
Yeah, 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 go ahead.
Yeah, so basically we can use one approach that is using two pointers,
Hmm.
and one is start and one is end, let's say. And then what we can do here is, so suppose start is starting from the first index at the zeroth index, and end is starting from the end index of the, suppose we have array height array.
Right.
So start is starting from this, end is starting from here, and then what we can do, while start is less than end, uh, what we can do here is, we need to compare the heights at the start pointing at start pointer and at the end pointer. So what how to do this, let's say we have height at start and height at end. Then we will find that we find the minimum height between start and end, and then we need to find the area. So that's why, so first find the minimum, that is using math.min at start and at end, and then multiply with the width of the start and end. So how to do this, that can be done by end minus start. So
Hmm.
this will give me the width of that particular region from start to end.
Got it.
And so this will give me the temporary area,
Mhm.
and we do this by using math.max, using current area and the maximum area till now. And then we need to move the pointers accordingly. So how how we can move the pointers? So yeah, so basically what I'm thinking is, if height at the start pointer
Hmm.
is height at the start pointer is less than the height of the end pointer.
Okay.
Yeah, start as less than, and end is greater than. So yeah, start is less than, then I will move the start pointer plus one, and if and otherwise move the left pointer, uh, and decrease the left point end pointer, that is minus minus.
Got it. And what's the time and space complexity going to be for this problem, for this algorithm?
Time complexity will be big of n. So basically, we are just moving in the single pass of the array. So time complexity will be big of n, and space complexity as far like a constant space. So because we are just using start pointer and end pointer, so we don't need any extra space for this algorithm.
So if we have to think about the brute force solution of this problem, what will be the brute force solution?
Brute force solution. Yeah. So brute force solution. How to do this in the brute force? So basically, uh, using two loops. For first for loop is going from 0 to the length of the array, and second for loop will go from I plus 1 to the length of the array.
Got it. All right, let's move to the next question. So we have to merge two sorted lists. How do we
Mhm.
go about that?
Okay, so to merge two sorted linked list and return it as a new list. Okay, and the new list should be made by this splicing together the nodes of first two lists. Okay. Okay, so two linked lists are in the sorted manner, and we have to give the output by merging these two lists in, and the merged list will be in the sorted order, right?
Yes, that's correct.
Okay. Okay, so is there anything like two lists are the same length, or might they can be a different length, right?
Yeah, they can be different. Then.
Okay, okay, okay. So what we can do here is, let's say one, two, and let's take one example, so it will be easier for me to understand. One, two, and four. Then one, three, and four. Okay. So here also I'm thinking like using pointers. So first pointer will be track. First pointer track the first linked list, and the second pointer will track the second linked list. And what I'm thinking is, so basically at the start of the pass, uh, both pointers are pointing at the two linked list, the head of the two linked list. And then what we can do, we can just compare that. That is, suppose head is starting at 1 and head is starting at 1, so compare them. If they are equal, then yeah, so I will also take one more pointer, that is, let's say it's a current pointer for forming the new linked list.
Mhm.
So, or else, yeah, yeah, let's say one pointer is for the new linked list, so that is current. And if both the pointer, that is first pointer and the right pointer, first pointer and the second pointer, uh, the value, if they are same, then
Mhm.
if they are same, then current at the current pointer we add that value. And then also current dot next will also be the same, because they are the same value. And we need to, can I write it over here, because I'm
Yeah, yeah, yeah.
not.
I've given the remote control. Take your time.
Oh, okay. Yeah, so what I'm thinking is, yeah, so basically let's take one example over here only. One, two, four, and one, three, and four. So first pointer is starting at this position, and second This is hard. And second pointer is starting at this position. So in the current, if they are the same, then what I'm thinking is current will be like 1 and 1.
Mm-hmm.
Then increment the first and second pointer.
Okay, let's take a case where you are having uniques in both the lists.
Oh, okay. So let's take this is a
Yep,
let's take this is a 3, and the second list is just 3 and 4.
3 and 5. Yeah,
Oh yeah, we can take 3 and 5 as well.
because both are uniques, right?
Oh yeah. So first pointer is right now on 3. Second is first pointer is at 1, and second pointer is at 3. Then 1 is less than 3, right? So first current pointer. So we add one node, that is first one,
Mm-hmm.
and the next, and what it will do. So we done with this one, then we increment this one, so it
Okay.
will point to the next. Then check that 2 is less than 3. And so if 2 is less than 3, then add 2 in this list, and increment the current pointer, and increment this first pointer as well.
Okay.
So now 4 and 3. So 3 is less than 4. So the right candidate is 3. So 3 will be here,
Okay.
and we
That,
increment
that,
the.
that works perfectly. So, sorry interrupting you because we have limited time.
Oh,
So,
no problem. Yeah.
if we have k-sorted lists like this, how would we solving that question?
Okay, so more than 2 lakh. K will be more than 2, right?
Yep.
Okay. Okay. So one approach will be like uh, do merging of 2 in the
Okay.
batch of 2, and so we will get the third list, then third and the fourth one, like that. And yeah, so this will also work. And one approach that is coming to my mind right now.
Let's stay at the first approach. So we'll be, if we have, let's say, 5 linked lists, then you'll
Uh-huh.
be merging first and second, and then,
And then we will get one linked list, that is the final one, the merge of first 2.
okay, yes, we got
Then
that.
yeah, we merged the first 2, then that result will be merging with the third one,
Okay, got it. And the result of third and the first result will be merging with.
with the fourth one.
Okay. Can there be any other approach?
So I was talking
Yeah, yeah,
about
yeah,
that
yeah.
approach as well. So basically what we can do, yeah, so we can use a priority queue data structure.
Okay.
For that, what we will do, we will keep track of the k elements in the priority queue.
Okay.
So at the first glance, we will add all the first pointer of the k list in the
Mm-hmm.
priority queue,
Mm-hmm.
and we will check that which one is the lowest one, which one is the lowest one,
Okay.
and
Yeah.
we will add in that way.
Okay. Which pointer we'll be moving? Let's say we have 3, 5, 2, 4, 7, and we have 6 and 8 here.
Mhm.
How will the priority key look like? A priority queue look like? Let's say this is a priority queue.
Okay. So what I'm thinking is we also need to keep track that whichever uh, this element is from the which list.
Okay. Okay. All right.
So basically, It will do one comma the position, the list of the one, right?
Okay, let's move to this one.
Okay. Lowest common ancestor of binary search tree. Okay. Of two given nodes according to definition of okay, the lowest. Okay. So 2 and 8 has the lowest common ancestor 6. Okay. 2 and 4 has the lowest common ancestor of 2. Okay. Okay. And what if one of the node is not present in the binary search?
Yes.
Then what should be my answer?
So, okay, that is an edge case. We'll come to that later. But we can assume that right now the node is always present.
Okay, node is always there in. Yeah, so both the nodes are always be there in the binary search tree, right?
Right.
Okay. Okay, so yeah, so one approach that is coming to my mind is so basically, let's say 2 and 8. So for 2 and 8, we will yeah. So what we can do here is we can keep track of the path from the root node. That is, suppose 2 has a
Mm-hmm.
path that is from 6 and 2, and 8 has a path from 6 and 8.
Okay.
So whenever the common node is encountered in this path list, then it will be like a lowest common ancestor.
Okay.
Let's say for 2 and 4.
Mm-hmm.
So 2 has a path 6 and 2, and 4 has a path 6, 2, and 4.
Mm-hmm.
So basically we go from the left end of the list, and we will check that whichever the common node that is coming right now, then uh, we can say that this is the lowest common ancestor.
Got it.
So in the 2 and 4, so first list is 6 and 2, and second list is 6, 2, and 4.
Mm-hmm.
So we check that from the end, that is from the end we have that 2 is the common element in both the list.
Got it.
So it will be like lowest common ancestor.
Okay. Can there be any other approach? What would be the
Mm,
order of that scenario? What would be the order of this solution?
uh, yeah, so basically it will be big of n as only.
Okay. Can we do better than that?
Yeah, so let's say it's a binary search tree, then can we do can we perform some operations that is basically made for binary search tree? Let's say uh, I don't think so. We can improve the time complexity in terms of n.
Think again.
But we can do one thing like mm, suppose current node is less than the so the suppose 2 is less than 6, right? Then we move to the left child, So we can do this in terms of left and right, left subtree and right subtree. So suppose both of them are in the left subtree, then just traverse to the left subtree only. Don't
Mhm.
go for the right subtree. But if both of them are in the different subtree, then it is making
Got
no
it.
sense of going like that.
Okay, take an example and explain what you're trying to say.
Yeah, so basically, mm, 2 and 8 is the example. Okay. So,
This is just I wanted to ask you, but take your example.
oh, okay. Mm, yeah, so basically, suppose 4 and 3 and 5 is the example. Let's take 3 comma 5. Then what we can do, both nodes are both nodes value is the less than the root node.
Mm-hmm.
Then we can definitely say that these two nodes are in the left subtree of the root node.
Mm-hmm.
Then for finding the path,
Mm-hmm.
we can just traverse the left subtree of the root node and don't go for the right subtree for checking the
Correct.
other possibilities.
Mm-hmm. Yep.
But if it is in the
And when
different
do we
subtree,
stop?
when do we stop?
Like, so when do we know that, okay, this we have reached the lowest common ancestor of 3 and 5? We are
Uh,
traversing through the left subtree, right? So 3 and 5 is less than that of 6, correct?
yeah. So basically, for then we need to find the path as well. So
Do we need to find the path? Think again.
yeah, suppose 3 and 5. So they are in the left subtree, and then what we can do? Mm, then also we need to find the path as well to find the lowest common ancestor, right?
Take hint, we don't need to find the path.
Okay, okay. So what we can do here is, so suppose we got the three in the
Hmm?
sub, in we got the three, then we just return the three to the root of that particular branch. So what I'm saying is, so suppose one is the root, one is a particular current node, and in that node, the left child is 3. Then we can return the 3 value to the left child of the current node. And so what we can say by this, the current node has a left child 3 and the current node has a right child 5. So if this is the case, then the current node is the lowest common ancestor for
Okay,
3 and 5.
got it. Okay, so let's say 3 and 5, and current node is 6. It is 3 and 5 are both less than 6, so we move to the left child of 6, that is
Yes.
2. And now what we see,
uh,
that 3 and 5 are lesser than 2 or greater than
yeah, so 3 and 5 are the greater than 2. So
2.
now 3 and 5 is going from to the left tree or left subtree of the 2.
That doesn't make sense. Left subtree of 2 is 0.
Oh, sorry, right subtree of the 2.
Okay, right subtree of the 2, and we come to 4, right?
We come to 4, yeah.
Then what we see?
So now 3 is less than 4 and 5 is greater than 4.
Okay,
Then what we can conclude that three is a in the left subtree of the 4 and 5 is in the right subtree of the 4.
okay. And what do we return?
Uh, Yeah, so basically from that we can return like 4 is a, so suppose no, but if, then 4 is also has some value 1 and 3.
4 has some
So
value 1 and 3 means.
no, I'm no, 4 cannot have 1 and yeah, so basically we reached the 3 and 5, then and so we are now at 4. So fourth left child is 3 and fourth right child is 5. Then 4 is the right candidate for the lowest common ancestor of 3 and 5.
All right. All right. So what's the order of this algorithm that we are using?
Yeah, so whatever we are using right now.
Yeah.
Yeah, so basically we reduce the search space in terms of left subtree and right subtree. So it will be a log n.
It will think again, but good try. So my follow-up question was is if it is not a BSP, then I think we have already discussed because we have discussed the parts. All right, let's take a 2-minute break. Okay, once we come back, and at that time you can share. I'll send you the Zoom link once again so that
Yeah.
we're not overshooting the time as well. So
Okay.
we'll be discussing one question. For that, we'll be coding as well. Okay.
Okay. Okay. Yeah.
All right. Bye bye.
Bye bye.